In this video, we're going to discuss convolution with multiple channels. In particular, we'll talk about multiple output channels, multiple input channels, and multiple input and output channels. First, we'll discuss multiple output channels. So as you recall in the first case, we had the image or tensor x, we performed convolution with a kernel, and then we got an activation map. So for multiple output channels, it's pretty similar, except for every output channel, we'll have our own kernel, and we'll produce an activation map. So let's do an example to clarify it. So we create a convolution object, and we'll create an image. And just to note, these two parameters here will be the input size, or number of images, or mini batch size, and the second element will be the number of channels, in this case 1. So let's perform the convolution and see the results. And just to note, because PyTorch randomly initializes our tensors, we're going to set some nice values up using convolution kernels people have already come up with before. So here's our input image x, and then we perform the 3 convolutions, and we get the 3 outputs denoted by z0, z1, and z2. And to make things a little interesting, let's convert the tensor into an image and look at the outputs. So we perform the convolution, and for each channel we have an output. Now if you look at these two images, they're basically a constant value. And if you look at the result of this image, it actually detects the edge. So basically, certain kernels can be used to detect certain features in an image. So let's see what happens when we apply a different image. So we'll create a second image, and we'll perform the convolution with using the same kernels. And here's the result. And as you can see, it's a horizontal line. And we perform the convolution using the exact same kernels. Let's take a look at the output channels. So in this case, these two kernels, nothing happened. The output of this channel detected the horizontal line. So this kernel is actually a horizontal line detector. So to reiterate, different kernels detect different features in the image. So just to note, we didn't really discuss the bias. So the bias is analogous to the linear terms. When we add the bias term in the convolution, we're simply broadcasting it to every element in the tensor or matrix. So basically in general, if we have 3 output channels, every channel will have its own independent bias term as well. Now let's discuss multiple input channels. So you might have multiple input channels in an RGB image, where each channel represents a different intensity of red, green, and blue. We'll have multiple channels in a convolutional neural network. So with multiple input channels, so for multiple input channel convolution, we'll have 1 output, and for every input channel, we'll have our own kernel. We'll perform convolution with that kernel with the corresponding input channel. We'll add the results together, and we'll get an output. I like to use a matrix analogy, where our parameters are like a row vector, and our input images are like a column vector, and we'll perform the dot product operation, but instead of performing multiplication, we'll perform convolution, and that helps me clarify what's going on. So let's do an example with 2 input channels, and as a result, for every input channel, we'll have a separate filter. And let's create an image with 2 input channels. Here's the image for channel 1, and here's the image or tensor for channel 2. So we'll perform convolution on the first channel, then we'll perform convolution with the second kernel for the second channel, and add the results together. And this is the final results. And that's it. Now we'll discuss multiple input and multiple output channels. So let's create a convolution object with 2 input channels and 3 output channels. So we'll have 3 outputs and 2 inputs. So basically all we do, for each output, we'll have 2 sets of kernels corresponding to each input as follows. And sometimes it's helpful to visualism like this. We'll have 2 input channels and 3 output channels. So let's see what happens. So for the first output, we have these 2 kernels, and we take our 2 inputs, and we perform convolution with those 2 kernels. We add the results together, and we have the final output. For the second output channel, we do the exact same thing. We take the 2 inputs. With each of the corresponding kernels, we perform convolution, add up the results, and we get the second output channel. For the final output, we have 2 kernels, each for the 2 inputs. we perform the convolution on the two input channels, we add up the result, and we get the final output channel. So I like to use a matrix analogy, where the actual convolution kernels are the different elements in the matrix, and the actual image or tensors are a vector. And just like a matrix, we have two inputs and the two columns, and three outputs represented by the three rows, and perform the matrix multiplication. And instead of multiplication, we're just performing convolution. So here's the formula for the multi-channel convolution, where L is the output channel and K is the input index. So let's see how the actual different kernels look. So we have the kernels for the first input channel, the kernels for the second input channel, and the kernels for the third input channel. And just to note, PyTorch randomly initializes it, but in the lab we came up with some nice values for you to use. So we'll create an input image, and the first channel will be the following image, and the second channel will be the following image. So now let's see the output for the different channels. So here's our equation again, and we'll just write down the expression for the first channel, and we'll set the bias term equal to 0. So for the first output channel, we take the first input, convolve it with the corresponding kernel, and same for the second input, and then we get the output for the first channel. Similar for the second channel, we do the same thing with two different kernels. We add the result, and we get the output for the second channel. And finally, for the last channel, we convolve it with a separate kernel for both channels. We add the results together and get an output. And that's it.